So I want to talk about sorting today, in particular about sorting methods in the Java library and what that has to do with research, with my research, and also a little bit what the life as a researcher is like. That will only come through in the talk in a tangential sense, but I welcome any of your questions about this too. And if you're a PhD student, of course, you will also be into that. You will have made that decision already. That's my outline for today. We'll start with some context about very broad what research in university is like and what research is happening in our department and what my research is about. And then we'll dig very deep on one particular example that I think is a very nice story to tell, and also a nice opportunity for you to engage if you're willing to do so. What is a university? Well, it's the place you're supposed to be at but can't attend now. Well, sorry for that joke, but another way to answer the question is, let's look at where the name comes from. It derives from the Latin phrase Universitas Magistrorum et Scholarium, where universitas is just the whole or everything. That's where the universe comes from. That was the original meaning, just a community of teachers and students. 200 years ago, roughly, Wilhelm von Humboldt, the guy on the right here, came up with the idea that universities should have both teaching and research in one place. They should connect the two, and they should ideally be a place where everyone can be both a learner and a researcher, because the two things are really very related. But I also understand that you might say, why do I care about these things? What does this 200-year-old guy have to do with me? It has inspired all the Western universities have basically adopted Humboldt's ideal to some extent. But what does that mean for a student who is starting in computer science today? I have a couple of reasons listed. The first two are basically saying researchers have to be into their topic, and that will help for teaching because they will teach you cutting edge stuff and will stay up to date. But there's a more subtle thing that I don't know how obvious this is to you as starting students. Research is where institutions, universities compete with each other. It's their main arena for competition. And these competitions are what attract people and money. It will follow the good research universities to a good deal. And that will help you. You will be working with interesting people, interesting other students. That has a lot of repercussions. So I think that's an important point. And last but certainly not least, it's a chance for you to get involved into research. Research might be the ultimate academic activity of the ultimate academic challenge. Work at the forefront of human knowledge, improve the knowledge of mankind. If that isn't exciting enough, I don't know what is. And being at a research university means you can, if you want, embrace yourself early on into research. The topic I'm talking today is very approachable in this sense. In fact, most of what I show you today has been my MSc project. And there's open questions that are totally in reach for you. You just have to work a little bit and engage with them a little bit. So I hope that this talk will also inspire some of you to see research as a potential career. So if you have any other questions about this, I'm happy to also talk about these. Before we move on, I'd like to have you engage a little bit again. And I'd like to ask you if you consider a career in academia as a possibility. By a career in academia, I basically mean being a researcher, but academia, of course, also comprises university teachers. They might also do research. They might not get as much time for doing research, but both could be a career in academia. Okay, you're very quick. That's great. I think that's partly due to Slido showing the stream right next to the polls. That's great that that works fine. Now I should have paid attention at the previous question what the total is, how long I should give you guys and wait for answers. I think 120 was roughly it, but seems like we're a little more now. Predominantly, you're saying maybe, but not sure yet. So that's perfect. That's exactly my chance today to convince you. That's totally fine. And 8% have essentially, well, not committed, but would like to do this. That's very, very interesting. All right. So let's see what this is about. On the next slide, I have a very nice illustration for you. I agree it's a little small, but there's a link in the slides. I can make the slides available afterwards if you're interested in following up on this. That's a map of computer science as a field with, roughly speaking, the more foundational research, theoretical computer science, engineering, how can we build machines that compute, and all the interesting applications of what these machines can do. And so it's very nicely done. Take some time. There's a YouTube video where Dom also explains all this in step by step and explains what's behind each of these topics. Very, very nicely done. I totally agree with his structure. In Liverpool, our department has particular strengths in AI and robotics. That's one big section where a lot of our researchers work. And a second is in algorithms. Algorithms basically up in that corner. Computational complexity, the very, very fundamental questions, which problems can be solved by a computer and how fast. And the more applied version of algorithms like I will talk about today. Not just which problems can be solved, but which is the best method to do so. My personal interests are mostly in these three areas. Let me try to zoom in a little bit on this. So we have algorithms here, which is, as I said, methods to solve a computational problem. The example that Dom picked here is sorting, which is perfectly on topic for today. Okay, that doesn't work. I have to use the scroll bars. I'll move. The second topic I'm working on is compression and working with data in compressed form. I will not talk about this today, but it's a very, very nice topic too. And lastly, the third topic I'm working on is data structures, connected to algorithms, but a slightly different angle on things. So I would summarize my personal research interests as algorithm science. I will talk about what I mean by that in a second. And as I said, computing over compressed data, if you store something so that it's space efficient, but you still want to be able to compute on it without decompressing first. That's what I mean by that. That's a very active field these days for reasons that will come up in this talk as well. And adaptive algorithms will be mentioned later in the talk. In a sense, they try to be smarter whenever the input allows them to. But for today, I'll focus on the first point. And here's what I mean by algorithm science. It's a bit of an attempt to bridge a gap between two fields that I see within algorithms research. And they are on one side experimental algorithmics and on the other side algorithm theory. And I'll briefly try to summarize what the field's goals are. In experimental algorithmics or algorithm engineering, people try to make a solution for a specific problem very fast as they can, on a specific machine, and for specific inputs maybe. They do experiments in the sense that they run the algorithm and measure how long it took, or how much space it took, or other resources that it took. The questions here are sometimes if things generalize from the one specific scenario to other scenarios, other input sizes, other machines. The opposite, in a sense, is algorithm theory, where the machine model is very, very generic, so that it doesn't, it's very, very abstract, so that the only statement that people usually are able to make are for the worst case input, and they only formulate them as a big O bound, which, if you've never heard of big O things, you will see that very soon. And if you do, then you will roughly know what it is. The problem with big O is that it ignores constant factors, and that means such a bound doesn't make a concrete prediction how long an algorithm will actually take on a specific input. So what's missing, and what algorithm science is about, is provide performance guarantees that make a concrete prediction, but still are as platform independent as is possible under these circumstances. And as will come up in this talk, it will consist of making a mathematical model of what is the cost of an algorithm execution. Hopefully that model captures modern hardware's features, but is still abstract enough to be analyzed mathematically, precisely, or by experiments. And the model should also be should be possible to validate the model, so that you can compare your predictions to actual outcomes. I know that sounds probably quite abstract if you're not familiar with the fields and don't have the examples in mind that I have in mind. It might not make so much sense, but after this talk, it probably makes more sense. Before we get started with this topic, I want you to be a little more active again. I'd like to see what sorting algorithms you know. Just write them in, fire them up. Doesn't matter if they're good or bad, or if you would like them or not. I'm just trying to get a feel how knowledgeable you are. I know there's a bias between the years, etc., but we'll see. So keep shooting, and let's see what we have. So there's a big bubble, which is one of the sorting methods with the catchiest names, but probably not the one you would choose because it's fairly slow. I see merge sort, I see quicksort in different spellings. Okay, the system could be smarter to merge these. And all sorts of other ones. They keep moving so fast it's hard to read. Amazing, guys. That's a lot of different sorting methods. None haha is also great. It's a perfect method. Okay, pretty cool. Thanks a lot for engaging with this. I think I'll just leave it open for the moment, doesn't hurt, but I will slowly move back to the slides. So a lot of people seem to know, or some of you seem to know a lot of algorithms. The data I collected with Slido now doesn't really tell me how many of you know which algorithm. But we'll get there. So much for the context. I now want to talk a little bit more about specifically the Java library and the methods that arise from that. So I use it as a case study for algorithm science, and I will point out at specific points where that methodology comes into the play. Java is nice because it has a single implementation of its library, a reference implementation that most people use. That's just handy. And what's more, within the last 15 years, all of its sorting methods have been rewritten from scratch. That's fairly interesting because you would think computer science started somewhere in the 40s or 50s of the last century, depending on who you ask. And sorting was among the first things that people solved. But apparently there's still new things to be discovered, so that it still makes sense to replace these methods. These are the two methods that Java uses. One is called dual pivot quicksort, and this is what we will talk about in excessive detail today. The other is called timsort. I have also interesting stories to tell about this one, but we won't have time for everything today. Both methods were developed by developers, by which I mean practitioners, programmers who are focused on getting a specific task done. They were both, in a sense, motivated from weaknesses in the existing library. But the focus in both cases clearly was get these methods fast on benchmarks and have unit tests for correctness. Not so much the mathematical approaches that I care about. I want to give a very brief history about Quicksort in libraries, essentially to put this within the last 15 years into context. Now, here below I have this, not totally serious timeline where everything starts with the invention of Quicksort by Tony Hoare. Then, without going into all these details, there's been flurry of changes and optimizations in the 60s and 70s still, and two isolated improvements in the 90s. But since then, basically all programming libraries used identical code for their sorting methods. If they were based on Quicksort, they were using almost the same method. And that's quite comforting, because it's, in a sense, says this was the way to go. This was the right way to do Quicksort. Until 2009 roughly, when Vladimir Yaroslavskiy, a Russian developer, started playing with Quicksort with two pivots. After a couple of more optimizations with others, it was fairly quickly announced in the public release of Java 7, and is now deployed on all your devices if they run Java. It's also the basis for the Android SDK, so if you have an Android device, its sorting method uses this algorithm. So it might actually be the most run algorithm to date. And all that after a fairly short method. Fairly short amount of time. So that's fairly interesting, I think. It raises the question, why would you do this? Maintainers of these standard libraries are very conservative because at all costs they don't want to break things. So why replace a well-tested implementation? Well, of course, because the new version was just significantly faster. Essentially, we go down from something like 9 to something like 7. And for sorting, this is like a major breakthrough. That's amazing. No one was expecting such a speed up. I should say that library methods are not the textbook algorithms that you learn in an introductory algorithms class. They have lots of bells and whistles added. And here are some that are used in this library. But in this case, it's not true that these make the difference. If you take away all these extra additions to the core algorithms, I will show code for the core algorithms, and it fits on a slide. That's as much as I will say. You still get this 8 to 7, 12% speed up. So something is going on with this dual pivot quicksort. There's something substantial happening, and you will, if you're anything like me, you're curious what's going on here. So I guess you want to know what this dual pivot quicksort is, after all. So because we have a lot of people who might not have seen an algorithm class, you might have had quicksort in school, but then again, I'm not exactly sure to what extent and how detailed. So here's my brief 1-minute explanation of Quicksort. Quicksort works as follows. It chooses one pivot element from the file you're sorting. Let's call that P. For every other element, we compare it with this pivot element, and then it could be either smaller or bigger. Let's assume we don't have equal keys, so there's never an equal case. And you can essentially put it on either side. Once we have determined what class each element has, we have to arrange the elements, so all the small ones go on the left and all the big ones go on the right. Once we have that, we can put the pivot in the middle, and that means this element will have reached its final position. That's the position P has to be in the sorted order. And then we can recursively sort the left and right part with the same procedure, as long as you have elements left. If you have a single element or an empty range, then you're stuck. That's Quicksort. Easy enough. The crux of the matter is how to get this step number 3 efficiently. And here again, I have a quick question for you to see how fast I should go about with this. You might have seen some partitioning method for this. Not sure. I will briefly show the one that's used in, or that was used in the libraries until Yaroslavskiy came along. But the pace, how fast I will go with this, might depend a little bit on how familiar you are with this already. Okay, I'll wait a few more seconds. It's roughly half the people have voted. Okay, it's jumping up now, even though the numbers don't move. I guess it's worthwhile to see the method in some detail, because many of you have never seen this. That's totally fine. All right. Yeah. Let's leave it at that. So here's an example, and I'll go through that in detail. But abstractly speaking, what partitioning is trying to do is again depicted up here. We have a list that's initially unsorted, and the values of the array elements is how high they are on this picture. And then afterwards, there is a pivot point, which means there's a point so that everything to the right is bigger than a line and everything to the left is lower than a line. So how does that work? That's what we want to do. Suppose we have this list of elements. We pick our pivot element, the leftmost. So far, so good. Now we want to compare elements with this, and we want to rearrange them as well. We'll do this with 2 pointers that move towards each other. I'll have to move a little further back. They move towards each other. One is starting at the left and moving to the right. So we start with this one. We compare our element that it points to with the pivot. It's smaller, and that's good, because on the left they should be smaller. So this element can just stay where it is. We move to the next one. That's obviously bigger, so there's a problem. We have to do something. In that case, we leave that pointer where it is, and we start on the other end, moving left. Again, we compare. Now, if it's bigger on the right, that's fine, because that's where it should be. But if it's smaller, that's again something we have to change. But now we have found 2 elements that are both on the wrong side, so let's just exchange them, and then they're both okay. That's how it goes, and then the left pointer starts moving again to the right, so same game as before, until we stop again, and then we continue from the other side, and ultimately the 2 pointers have met, and we have found the position where the pivot should go. So we can just swap it into this place, and then we're done. That's the method that the library used before. It's particularly neat because whenever it does a swap of 2 elements, both are put into the correct position. That's fairly smart. And apart from that, it just has visited all elements once by moving these 2 pointers together until they meet. Okay, I hope this was helpful and people feel more confident about this way. This is probably the method that you have seen or will see in an algorithms class. Now, what changes if we go to dual pivot quicksort? On that conceptual view, not that much. We choose 2 pivots instead of 1. Well, I guess you were expecting that. Then for every element, we have 2 pivots we compare with, and there's 3 different outcomes. It can be smaller, medium, smaller than both, larger than both, or between them. And of course, we have to rearrange according to 3 classes, all the small ones to the left, the medium in the middle, and the large ones on the right. And then we recurse on 3 parts instead of 2. I guess that's fairly natural and fairly straightforward. Again, the interesting question is how to do this rearrangement step efficiently and without using extra space. That's what in place means. And that's the innovation that Yaroslavskiy came up with, or I'm calling the algorithm YBB for Yaroslavskiy, Bentley, Bloch, because that's the 3 people who worked on it. But it's fair to say that Vladimir is the one who had the lead or pushed that idea forward. I promised actual code for the algorithms. Here it is. It is kind of pseudocode as it's written, but you can translate this very easily just to C or Java, whatever you like. This is the classic quicksort. All the interesting things are going on in this loop. That's what's implementing the partitioning. Everything else is just, well, we have to stop recursing at some stage and we have to recursively call ourselves. That's all fine. But the partitioning is the interesting part. And here you see there's the green pointer starting from the left and the blue pointer starting from the right. And when they have met, then we break. That's exactly this if. That's all there is, and that's exactly as I've shown it in the example. What you will notice is it's very sleek code, very short, very concise, and symmetric in terms of left and right. It's a nice algorithm. Now, once we finished, we will have scanned the array exactly once, some elements from the left and some from the right. But that's it. This is what Vladimir came up with, and even just from the optical impression, I think it looks much more messy. Again, the main partitioning is done in this loop, and you can again see there's different pointers moving. There's one from the left to the right, one from the right to the left, and a third one, this purple one that's lagging behind. That's what this picture shows. It's just a first impression that this algorithm looks more complicated, and you might question whether that's worthwhile doing. To help you understand how it actually works, I want to go through an example again. So we have, again, a list of numbers, and then there will be the pointers moving around, the green and the blue one. The green one starts, and now what is to be done is shown in the picture above. So we start comparing, as this box says, to the small pivot P1. In this case, we're bigger, so we follow that branch. So we're here, and so we compare with the bigger pivot. And that brings us to that point. We found a medium element. That's true. 5 is between 3 and 6, and medium can be skipped for now. That's what this tree tells us. And then we move on with the green pointer. So we do that. Another time, this time we find a small element, and for these, the rule says swap it with wherever the purple guy points to. So we do that and move both further. And as you'll see, we will always have the purple guy separate the small and medium ones, and K will move further into the unclassified region. All right, another time, this time we find a big one. That's the case when previously we started swapping. So here again, we do the same thing. We pass the control to the pointer from the right, which does its own thing. It looks similar but a little different. In particular, the big elements can stay where they are because they're on the right. But if we find, for example, a small one, we have to move it to the left. And this is the most complicated case that can arise. We have the 2, which should go to the very left. The 5 should actually be in the middle, and the 7 should go over there. So you have to rotate these 3 around. But other than that, it's not too bad. So we do this and move on. One more time. And then we notice that, again, the 2 pointers have met. So we have finished our partitioning. If you have paid attention to this diagram at the bottom, you will see that this is the invariant that we maintain during this, and at the end we will again have the green and blue pointer will scan the entire array once, and then there's another part that the purple travels over. This picture at the bottom is all you will need for this from this algorithm to follow the rest of the talk, but I feel it's helpful to go through this example in detail to see what's happening in this new algorithm. And hopefully you could follow, but you could also appreciate that it's a little more involved than the single pivot version. All right, that was partitioning. What's left is putting the pivots in place and recursively sorting, but that was as before, as I said. Now, you've seen this algorithm. You've seen both the classic one and the new one, and I'd like you to briefly think and tell me on Slido what you might guess why this new method is faster. We've seen it's faster. That was confirmed in running time experiments. People reproduced that result on different machines. It was the same result in different instances. So something is going on, and the effect is strong enough that I don't believe in very, very minor things. There must be some substantial reason. So I'm looking forward to your guesses for what that reason could be before I'll move on and tell you a bit about what I found out about it. Okay, so this is a lot of good answers. I will only roughly pick out some. Less processes, multiple swap at the same time, sorting one number against 2. Effective use of resources is great, but be more specific. Numbers are being categorized into 3 groups instead of 2. That's true, but we do that with a more complicated procedure, so it's not so clear what happens. Okay, I will keep this open. This is awesome, but I think I didn't expect so many good answers, so I won't have time to discuss them all. More swaps. Yeah. All very interesting suggestions. Keep thinking. We will get there. You will have some more time before I tell you the actual answer. So this is the algorithm. That's the thing I want to study. Now let's come back to algorithm science a little bit. The methodology of algorithm science says, now you have these 2 algorithms. You'd like to answer why one is faster than the other. Let's try to find a mathematical model that predicts the running time well and is analyzable. So we have to find some measure of cost for the execution of such an algorithm that matches what we see and is intellectually still manageable. The traditional choice for sorting algorithms that people have successfully been using for decades is count the number of comparisons. Whenever we classify elements, we have to compare them with pivots, so that's a well-defined thing to do. And it's definitely the first thing we want to know about this algorithm, so we might as well analyze the number of comparisons it takes. As you might know, Quicksort is actually a bad algorithm in terms of the worst case, so everything I will say is about the expected case, the average case if you want. That's something to keep in mind. But you can randomize the algorithm so you can force the expected case in a sense. So it's all fine in practice. but something to keep in mind. This is algorithm science, not algorithm theory. For analyzing these two algorithms, I will just look at the first partitioning step. Then you can solve a recurrence to get the total number. The main thing to look at is how many comparisons do I need for the first partitioning step, the very first I do. And I can ask the question per element. Well, how many comparisons per element do I need for one classification? Obviously, either 2 if I'm in one of those 2 cases, then I had to compare with 2 pivots, or just 1 if I was lucky enough to end up in one of these cases. So the sensible question is to ask what's the average number of comparisons per element. Now here's a simple back-of-the-envelope calculation. We have to be in one of those boxes, so we might as well take the green one, compare with the small one first, and if we have to, also with the second pivot. So 1 for small, 2 for the rest. And if you assume that everything's equally likely, and that's actually fine to assume if you randomize, we would expect the same number of small, medium, and large elements in total. So that's a third each, which means that averages to 5/3 comparisons per element. I guess that sounds plausible, and it's a good first approach. The problem is it gives the entirely wrong answer to this question. And the reason is qualitatively that there are correlations between two things, and it has to do with the fact that we have these green and blue pointers and they act differently. So as a thought experiment, suppose there's many small elements because the 2 pivots you picked are fairly large. We don't know if that's what's happening, but it could happen. Okay? So suppose that happens. If that's the case, then it also means that this green range is bigger. That's just from the definition of our invariant. And that means, again, in turn, that we will have this green tree more often, and we're more often in the lucky case with the small elements. If that was the only thing that was true, it could average out with, if we have many large ones, that they're expensive down here. But look what happens if we have many large elements, then automatically the blue range also gets big, and we use this tree more often where the large ones are cheap. So with that argument, even without doing any computations, it's clear that we will have this cheap case more often than a third. We will have more than 1/3 and cheap elements. So we will get less than the 5/3 comparisons per element. The question how many exactly is a very interesting one. And usually this talk would now go on with quite an amount of math. None of it is very, very complicated. It's totally fine and possible to follow with school mathematics plus a little bit of combinatorics and probability. But for today, I want to hide this behind the curtain and just jump right to the results. But again, let me stress that, peeking behind it a little bit again, this is the part where a substantial part of what I'm showing here was my MSc project. It's totally in reach of doing this as a student researcher. So if you find this in this line of work interesting, keep that in mind and be in touch. So time for the competition. We have 2 algorithms, the new dual pivot quicksort, the old standard quicksort, the classic quicksort I showed you. If you analyze the comparisons, you actually find that the dual pivot quicksort saves comparisons. It's only 5% less, but even still that's something. It was quite unexpected. And interestingly, if you went back to our analysis and took this simplistic view, the 5/3 comparisons per element would give you a 2 here, and it would completely hide this improvement. But if you do the analysis of this asymmetric treatment of left and right, you find out that it's exactly 19/10 times n log n comparisons asymptotically on average, whatever that means, if if you're not familiar with this. Great. So, end of the story. It was nice to have you here. The only problem is there's many other potential measures of cost. Remember, algorithm science is about coming up with models and validating them. And it just happened that comparisons didn't quite correlate with the running times as well as they should. And if you go to other things, this is essentially counting the assembly instructions of the Java language. Then you see that this actually, it sucks. The new method uses more instructions, not less. That's weird. Now, okay, if I go through all your answers to the question from before, maybe I find one along these lines, which is a feature of modern processors. They execute instructions not step by step, one after the other, but they pipeline them. They do part of the first instruction, and then the second part of that instruction is in parallel to the first part of the next instruction, and so on and so forth. But if you have conditional jumps, all this gets out of sync and you have to flush that pipeline. That has a cost, and that's known as branch misprediction cost. I won't have time to explain this in detail, but I did analyze the effect in detail. And I love how pi comes up as the exact solution of an integral in there. Again, these are all analytical results. You can prove these correct in the model taken. In terms of explaining why one method is faster than the other, they're completely inconclusive. Essentially, branch mispredictions don't make a big difference here. So that leaves us a little puzzled. What is going on? Now, I think I want to ask you again the same question as before, just to see if maybe you have changed your mind. I will keep the question just open and running, but in the interest of time, I'll first move on, and maybe we'll look at some of your answers later. Think about it. You've seen some of the results. Maybe now you have a different understanding of the algorithm and what might be the reason. If you don't see why, don't feel too bad. I didn't see it for years, despite working on this, and it was a great puzzle at the time. I will also show you that in hindsight, it's completely obvious. It's very clear. Once you see the solution, you will love it because it's very, very clear that this must be the reason. But let's see. I see very interesting suggestions. I don't think I've seen the exact right answer. We'll come to it. What happened? Comparisons, write accesses, the number of bytecode instructions, branch misses, all happens inside the CPU. I guess at this point I should stop the poll to not include more of the answers after I revealed it. But before we can actually do something inside the CPU, we have to get the data there, and that takes time. Some data on that. This plot shows benchmark results for CPU speed, where each point is one machine at a certain point in time where the result was reported, and the height is the speed of CPU. Some measure of that. Let's not digress into that. Note that the scale is logarithmic, so whenever you go from one tick to the next, it's a factor of 100 more. Which means from, the mid-90s to now, we improved by a factor of 10,000 in computing speed. It's amazing. Well, if you take the trend line of that, you get some 50% growth rate per year. That's roughly what Moore's law predicts. This is probably no news to you. We also can do the same thing for memory bandwidth. So that's the amount of the number of bits you can get from main memory to CPU per unit of time. That has also grown. But if you notice the numbers, it grew not quite as much as CPU speed. So there's a growing gap between the two, and the gap, this is a logarithmic plot, remember. that gap is exponentially growing. Not at a very great rate, but it's growing. And another way to show the same numbers is for every machine, divide the CPU speed by bandwidth. That's what these points show. And then the trend line here also shows that this imbalance for each machine is growing. What does that mean? It means at the time when this classic standard Quicksort was engineered and tuned for the library at the time, for the C library, the focus was on CPU costs, and that was right as such, because one memory transfer just costs 7 instructions in the CPU, and these instructions are very, very fine-grained. But by now, the weights have shifted to roughly 4 to 5 times as much. One memory transfer costs 30 instructions in the CPU. So now it doesn't make too much sense to focus on CPU cost only. You have to take the bandwidth into account. Well, and that's the last line in my table. If you take something that's essentially measuring the number of memory accesses that we do, which are not immediately cached, then you see this massive reduction in cost for dual pivot Quicksort compared to the previous one. So there's a single convincing explanation for running times. The number of memory accesses can just be reduced with using 2 pivots. And that also explains why this method has not been used earlier. It was not faster back then. They might have actually done experiments with a similar method, not exactly Yaroslavskiy one, because it has a few novel twists to it, but had they used some version of dual pivot Quicksort, it might probably not have been faster. Pretty cool. One last thing to add to this is there's a very intuitive and easy way to see why 2 pivots are better. And that's a little thought experiment. That's the last technical part I want you to dive through. Suppose you do one partitioning round. This is your array, and you partition it with this complicated YBB partitioning method into 3 parts. In terms of memory accesses, what you did was you scan the array once with the green and blue pointer, and you scan a third in expectation again with the purple pointer. You can get the same result if you do 2 rounds of classic partitioning, where you first split according to the large pivot and then only that left part again, but this time using the small pivot. If you use the same pivot values in each case, the result is exactly the same. Actually, the number of comparisons is also almost the same, except for these asymmetries. But more importantly, here you have scanned the entire left part a second time, whereas here the middle part wasn't scanned another time. That's the big difference. That's why using 2 pivots in one shot is more efficient than using single pivots. And I think that in hindsight is very obvious. It's an effect that's well known from other methods, but it hadn't been observed for Quicksort before. It needed the weights for memory transfers to be shifted like this. Alright, that's almost it. A very brief look beyond what we've covered is, if you think about this, I'm sure one of your questions was, well, how about more than 2 pivots? How about more than 2 pivots? You can do the same analysis I did. That's what I spend a lot of time with. Without going into any details, what you find is if you increase the number of pivots, comparisons are hardly improved, but the memory transfers do see improvements. There's one counter effect. So if you look just at memory transfers, the more pivots, the better. There's a counter effect that if you use many pivots, the code becomes very big and complicated. So probably there's a sweet spot between 2 and 7 pivots, something like that, where the exact sweet spot depends on a lot of details and is not so clear to say there's a single optimal number of pivots for any application and machine. Let me briefly say again what I've just told you. You've seen asymmetries in this algorithm, the left and right difference, and that's saved a few comparisons. You've also seen some evidence for memory transfer costs being more and more important in sorting as in many other problems. And you've seen that among the known optimizations of Quicksort, I didn't talk really about those, but I've studied many of those in great detail. And there's only really using several pivots is the only one that saves memory transfers. All the others improve other things like number of comparisons or overall cost in the CPU. But you need several pivots if you want to bring memory transfers down. I have a lot more to say about this algorithm and its friends and relatives. Not for today, but feel free to chat about this at some other state, at some other point. I think for today, I'll leave it with that. Like any scientific talk, there should be time for question and answer. Because I played with the Slido thing a little bit too long in the beginning, we don't have as much time. So if you have to rush, let's postpone the Q&A a little bit, and instead I want to do the takeaway quiz with you. So the quiz is now open. You can join. So you just type in your name. It's very short. It should take just 1 minute. And then we can call it officially over. So great. People start joining. It will just be a very quick test on what I just said. Fairly easy, I guess. But it's a little fun exercise. Keeps you engaged, and moreover, there will be a scoreboard at the end. So we'll see. I'll give you a few more seconds to join this. Yeah, still more people coming in, so I'll give you a few more seconds. So while we're looking at that, there was lots of questions in between. A particular one I wanted to point out. I'm happy to continue and go through all the others too, if you want to. If you want to contact me, I can update the Canvas website with A, the slides, that was another question, and B, a link to me on Teams or email. So if you have any further questions, please be in touch. If you liked any of the type of research, I have open problems related to this, approachable for students that are somewhat math savvy, but there's also experimental work if you're more on the implementation side. Definitely please be in touch. Then we can try to find a project for you. Okay, how do I activate the quiz? So here's the first quiz question. You will have time to answer that now, I hope. I guess you need some time to read the questions, a little lengthy. Okay, and I want to cut everyone out from the quiz, so I guess I'll leave it open for one more moment. There was quite a bunch of people upvoting the question "You lost me at hello." That's fine. That's partly intended, not intended in the sense that I want you to suffer. But a good research talk should actually have a part where the audience is very challenged. That's part of the genre, if you like. It's also, of course, a consequence of the very mixed audience. I wanted to give the more advanced students some food for thought, while at the same time I tried to include some basic things. So if 30 out of 130 say they couldn't follow, I have to be happy with that. Okay, I think we'll move on to the next quiz question. So here's what people voted. And here are the correct answers. You did well. And here comes the second question. Okay, still more people voting. I guess this one was... Maybe I made it too easy. All right. Still some more coming. I'll give you 5 more seconds for finishing the quiz. 5, 4, 3, 2, 1. And I guess another 5 seconds because the stream is delayed. So here's the votes. And of course, that was the main reason. That's it. Nice. And here you see it's not only getting it right, it's also getting it right fast. Of course, it was way too few, way not enough questions to really have more than many people will have all correct. That's totally fine. Thanks for attending this. I'm happy to continue with more of the Q&A, but I also see that we're over time. So I'm happy to go through some of these questions. If you want specific questions to be answered earlier, then use the upvote feature. I'll try to cover some of these. Don't spend too much time on either, but there are many interesting questions. It's probably worthwhile talking about these a little bit more. I would love to have this Q&A session over Zoom or something like that, but I didn't know of a very good solution to integrate the two things seamlessly without spending another 10 minutes till everyone is on Zoom. So you have to be typing for that one. So let me pick that one first. I didn't understand half of this, but it was a lot more interesting and interactive than any of the other online lectures I have attended. You will attend many more and they will get better. It's tough to make it interactive and interesting. it's also tough to make it understandable and interesting. That's particularly challenging. Well, thanks. I'm glad you liked the interactive part. This is about the new change in our program to move away from Java and move to Python. The move is very sensible. Python is a good language too. You will probably not learn Java in the compulsory courses, as far as I know. But I mean, learning another programming language on the side is not as hard. You will definitely also do a project where you can use another language. I think there might be some chance to have some modules cover, this is how you would do it in Python and this is how you would do it in Java. But I guess, strictly speaking, the answer is no. You will not have to learn Java in the classes, and that also means the opportunity for that is a bit limited. How many pivots can you have? Does having more pivot further decrease sort time, or does it increase? Probably the answer to that was at the end of the slides, and you posted it earlier. There's definitely diminishing returns on top of the effect that the code becomes bulky and big. I haven't seen very promising things beyond 3 pivots yet, but there's a method with 3 pivots that could be promising. I've discussed this with Vladimir, but he was very, very focused on 2 pivots, and I think at some stage he said he's probably not able to do a good 3 pivot quicksort because he likes 2 so much. So much for that. But there's other languages. Often what libraries just need is some enthusiast who just goes ahead, implements a good version, and convinces people to use it. So if you have a favorite language and you think the sorting methods suck, go and make it better. It's totally possible. I'll put the slides on Canvas, or put a link on Canvas. Definitely no problem. Kotlin nowadays, I guess you mean in the programs in general instead of Python. Well, there's a good point to be made for every language. I like Kotlin without having it used much. I learned Java and I was working as a Java developer for some time. So I'm JVM biased, maybe. Who knows? What the hell happened to the... Okay, this is the slide with all these dots. Maybe we can find the particular one. But the quick answer is the slide should be taken with a grain of salt because it mixes very different types of computers. So, but it's an interesting question, so I want to address this. Okay, this one, I don't know about this one. I think this one is a Raspberry Pi. And I suppose these ones on the upper front, they must be supercomputers. Because at the time, this probably wasn't achievable in a desktop. The problem with this benchmark is it mixes different types of machines in one data set. So you have the big range from embedded devices to the best supercomputers. Or, well, not the best, but big cluster computers. And I just took the numbers to get a very, very big picture. So don't take the exact number here, the 46%. Don't take that too literal. But the trend is undeniable. C#. I have no clue what the library in C# is like. And one problem is that it might not be open source. But I might be wrong. .NET got a lot more open. It's quite possible. I don't know from the top of my head. It's intuitive. You don't like the complex diagrams. I guess I lost the context for that. I agree, in general. Are there any sorting algorithms faster than dual pivot quicksort? That's a very interesting question. There absolutely are. The question is a little bit, what is the game that we play? How does the competition look like? I've just last week read a 70-page, I skimmed the abstract off a 70-page paper that was published by a group that compared around 20 implementations of different sorting algorithms in lots of different scenarios. The quick answer is it's hard to find a single algorithm that performs well for every possible scenario and machine. Usually, generic methods like dual pivot quicksort can be outperformed if you're willing to use machine-specific instructions and non-portable code. If you're a low-level hacker in C, C++, like these guys from Karlsruhe, they're extremely good at that, but they admit that some of the stuff they do is not portable to other machines. It has to be a specific CPU, etc. So you can definitely have a faster implementation. A faster algorithm on the conceptual side depends. For a generic sort, not easily. Yeah, an interesting comment about big O can be harmful. Thanks for attending. I appreciate the feedback. If you have X, great. Okay, this is exactly the cases where you only need the single comparison, I hope. So maybe that part is clear by now. Further reading for people who are interested and see their future in this field. Okay, I'll shamelessly point first to my own stuff. So I've written a couple of papers on specifically Quicksort and its friends. Honestly, I wouldn't recommend you to start reading with those because these are research papers written for experts. There's better introductions to the general field of the analysis of algorithms. There's a book essentially called Introduction to the Analysis of Algorithms, which is fairly good. I'm happy to post some pointers on the Canvas page. If you're very interested, maybe the easiest thing is come and chat. As soon as we're allowed to chat. Oh, well, we can chat over Teams. Why not use tri-pivot? Yep, maybe. In Java, it seems dual pivot is faster. The exact trade-off is in general hard to make. It depends on details then. Is it possible to make a branchless sorting algorithm? That question is, in a sense, tricky. It depends on the model. If it has to be comparison-based, it still is possible. The simple answer to that question is a big yes. It's always possible to make any program whatsoever completely branchless, but the general construction is costly and usually leads to crappy code. There's a paper on that called Lean Algorithms, if you're interested in that. But specifically for Quicksort, colleagues have implemented a version that avoids conditional branches, and that actually helps very much in certain scenarios. I would still call it essentially Quicksort. It's essentially the same idea. It's called Bloch Quicksort if you're interested. Applications of sorting algorithms, well, in popular technology is sorting is an elementary building brick of all kinds of more interesting algorithms. I mean, every graphical user interface uses sorting to display things in a reasonable way. All file systems, whenever you open anything that is a list, it's usually sorted because people hate things in random order. But then there's many other algorithms that people use all the time. Well, I'm not sure if I should start a comprehensive list of this. Sorting is particularly important in computational geometry. So everything with computer graphics ultimately has to sort things. It's used in so many ways that it's hard to name one specific application that sticks out. I think that's the main thing. But if you improve a sorting method, that these improvements will very likely yield to further improvements down the line. And finally, the recording of this presentation is just where you are. If you grab the YouTube link, you can keep that one, and I'll also post it on Canvas. The same live stream, you can just rewind and watch it again. The only thing is that the Slido page will probably cease to exist at some point. Now, the link from Canvas should actually be permanent. The short link with this meeting code, that one is gone at the end of the meeting, but the link that you used from Canvas remains active. Okay, great. I'm not sure if anyone is still here or if I scared you away. I actually wanted to do an exit poll. Not sure how many people are still here and care for filling it out, but I'll just leave it open for those of you who are brave enough to listen to me 20 minutes answering Q&As. Oh my gosh. Thanks so much. I hope this was interesting, entertaining, and a bit useful too. Be in touch if you like research. Be in touch with others if you like research, but not mine. Take this opportunity. You're at a good research focused and strong in research university. Make use of that potential. Bye guys. It was good having you here, and hopefully see you soon in person. Bye.